So today we'll start our session with what? Understanding transformer decoder. Okay. So this is the diagram that we have discussed in the last session, right? So this architecture is the main building of the transformer block. Okay. So when I talk about this architecture, we have two important blocks there. This is the classic transformer architecture. Okay. When we talk about the new transformers that we are using these days, like GPT-4 and all that, the functionality would be more or less the same inside encoder or the decoder blocks, because as I told you, we have only encoder based transformers, only decoder based transformer, encoder decoder based transformer. Whatever it is, the inside functionality and the procedure would be same with some modifications in the architecture. Okay, so if you understand this, you can easily understand any architecture that comes your way when we talk about different versions of transformers or whatsoever. Got it? So, on the left hand side you see some terminologies, right? So in the last class we have done till what? We have done till encoder part. We have seen what is tokenization. We have seen what are input embeddings. We have seen what are positional encodings. And then we have seen the attention block where we start with generating query key value matrices, and then attention mechanism, self-attention mechanism applied to it, and then adding in normalizing batch, and then we have seen a encoder. Okay, so today our focus would be on the right hand side of the diagram. Okay, the left hand side, that small part is what? The encoder one. On the right hand side you can see another block which is what? Decoder, which would be our topic for today. Okay, so we have covered that encoder block. We will be discussing about what? The last decoder block. Okay, now before I start with decoder, I'll quickly recap what we have done in encoder, because more or less the decoder is also same like what? Encoder in terms of the blocks inside and functionality with little changes. Okay, so I would like to focus on the overview of the encoder first for a while, and then we will switch to understanding what? And we'll switch to understanding decoders. Okay? Yeah. So what did we see in encoders? When you look into the diagram, yes. When you look at the diagram, what are the two important blocks that we have seen in encoder? One block is called as what? Multi-head attention, and the second block is called what? Feed forward network. Okay, the same thing we are talking here. The encoder is the first part of the transformer and is responsible for processing the input sequence and generating what? What is the input to the encoder? The input sequence that I give. What is the input to the encoder? The input sequence that I give. What is the output of the encoder? Features. What features? The context-rich features. When I say context-rich features, I was talking about one example of bat, right? Two bats. What are they? Cricket bat and animal bat. So what exactly that bat represents in the sentence is understood by the context. That is the meaning of that particular word in that sentence. Okay, that is understood when you apply attention mechanism. So when I talk about encoder, the input to the encoder is a input sentence, and the output to the output of the encoder is what? The context rich features or context rich embeddings, I say. Okay. Now each encoder block consists of two sublayers. What are they? Multi-head attention is one block, followed by feed forward network, another block. Okay. Each layer is again followed by what? When you look into the diagram, we have multi-head followed by what? Add and normalizing. We have feed forward followed by what? Add and normalizing. That's the same thing I am writing here. Each of the layer is again followed by what? Add and normalization block. Okay. The encoder does not have a look-ahead mask because it processes all the tokens in parallel without restrictions. This point is very important for us to understand the decoders. Okay. Now when I talk about RNNs take sequential data, right? One word at a time. That is the reason we have this long range dependencies problem. So when I talk about attention mechanism or transformers, all the input tokens are passed simultaneously or in parallel. Yes or no? Okay. So when I talk about all the input tokens getting processed parallelly, I don't mask it. When I talk about masking, in the attention mechanism we have seen a diagram. In the scaled attention we have seen a diagram. Okay, look at that. First I have matrix multiplication followed by scaling. After that I have masking, which is what? Optional. Why am I not masking? Because I want to process all the input tokens at a time. I don't want to hide any input tokens. I want to process the entire input sequence at a time. Yes or no? So that is the reason when I talk about attention mechanism inside encoder, I say masking is optional. Yes or no? Did you understand why masking and enti? Hiding. Okay. I don't want to hide anything here because I want to process all the tokens of my input parallelly at a time. That is the reason in attention mechanism of encoder we do not mask the inputs. Okay. So what is the last point that is written? The encoder does not do any type of masking because all the input tokens will be processed at a time. Okay. Now, what was step 1 in encoder? First we take the input sentence, we find the input embeddings of that, we find the positional encodings of that, and then we add what? Input embeddings with what? Positional encodings. That was step 1 that we have seen. Okay. Now, what is the input that we are giving to the encoder? Let's call it as X. So X is equal to I am Asha, I ate an apple, I love AI. Whatever the sentence you give, that is represented as what? X. For our understanding, just know that what is X? X is the input given to the encoder, which is nothing but a sentence or a sequence. Okay. Now when I look into step 1, each token in X, what do you mean by token in X? When I say I am Asha, I is a token, am is a token, Asha is a token. So all these tokens in X are first converted into what? Dense vectors. What do you mean by dense vector? N-dimensional vector. When I say I am Asha, I is converted to n-dimension vector. Am is converted to n-dimension vector. Asha is converted to n-dimensions vector. Why? Because that bad. When I talk about bad may be what? Multiple meanings. Okay. When I talk about Asha also, Asha can be a name. Asha can be what? Asha can be what? Hope. Whatever it is. Okay. So what exactly is this Asha in this sentence? Means what? So when you say I am Asha, I am teaching. So this Asha means what? A name. Otherwise, that Asha can be something else. Okay. So how many possibilities of Asha are there? We exactly does know. Okay, 1 or 2. But when I process my English sentence, there may be multiple meanings for each word, and the context of that word would differ based on the sentence that I am using it. Hence I take a dense vector for every word. Hence I take a dense vector for every word. Okay. So we do that and use an embedding layer for addressing that. What is this embedding layer? Embedding layer is nothing but the word vector representation of each token. What is embedding layer? Word vector representation of each token. This is step 1. Again, what do I do? The transformer does not have recurrence because all of them are getting processed parallelly. So I am Asha is different from Asha am I, and it is also different from am Asha I. Yes or no? Are the 3 sentences giving you a correct meaning? No. Which sentence is giving you a correct meaning? I am Asha. Because this is in sequence. So if you want to get proper output, when I talk about language translation, I am Asha ante Telugulo em ravali? Nenu Asha or na peru Asha or what? My name is Asha ante na peru Asha. Okay. Now if you want to get this correct translated output, I have to process my input in what? Sequence. That is order. Okay. when I talk about RNNs, ఒక్కొక్క word simultaneous ga ravatledu. One word at a time is coming. So there I don't bother about the sequence because one word after another word is coming. But here what is happening? All the words are generated parallelly. So order of the sequence, order of the words is important, which is taken into consideration by position encodings. So in step 1, we take the input sentence, generate the tokens, generate the word embeddings of that, generate the position encodings, and add what? Word embeddings with position encodings. That is what we have seen. Okay. Now how are we generating positions again? By using sine cosine function. After that, the results in the embedded representation of the input are ready for processing. Okay. What is the first block inside encoder? Multi-head attention. Okay. Now when we talk about multi-head attention, the input X that I am taking is passed to the first block, which is called as attention block. Okay. Inside attention block, which mechanism am I opting? Self-attention mechanism. Can you see there? The input X is passed to a self-attention mechanism. Each token attends all other tokens. What do you mean by self-attention? One word is compared with what? All other tokens. This is called what? Self-attention mechanism, such that the importance of that word or the meaning of that word would be depicted. Okay. So multi-head attention is what again? Same type of attention mechanism repeated for n number of heads. N number of heads. So we call it as multi-head attention. Okay. Now what would be the output of MHA? Input to attention block is what? The input sentence, that is tokenized position based word embeddings. What is the output of MHA? What is the output of MHA? Input is query key value to MHA. What is the output of MHA? See, understand. X is input. Can you see that last block on the left hand side, inputs? That input is I am apple. What am I doing to that input? Generating input embedding and position encodings. Okay. So now I have this I am apple converted to tokens. Those tokens, each token will have word vectors and positions. That is given to what? The first block, which is MHA. Now when I am first giving the inputs, I don't know what apple is that, or I don't know what ASHA is that, or I don't know what bat are you talking about. After you give it to MHA, where each sentence or each word is understood by other word comparison, we will understand what bat are you talking about, what ASHA are you talking about. Initially, the input does not have any meaning depicted for each word. After you give it to attention mechanism, we will understand the context of that word in the sentence. So I say, what is the output of MHA? The output of MHA is what? A refined representation of the input sentence. What do you mean by refined representation? Refined and filtering. Refined oil and what do you mean by that? Filtered one. Yes or no? So basic raw input is taken, that is processed in MHA, and now MHA is capable of understanding every word. So we call it as what? The output of MHA is what? The refined representation of the input sequence, where each token has what? Context from all other tokens. Are you all clear now? First input ki meanings telidu. What is ASHA? What is bad? I telidu. Once you process it to MHA, MHA will understand what? The context of the words, which is called refined representation of the inputs. Okay. Now what is the second block? Feed forward neural network block. Okay. So why do we use feed forward? To introduce non-linearity such that I can depict the words. Okay. So here when I talk about feed forward, we use two layers. One is called FC1, second one is called FC2. What is FC1? Fully connected layer 1. I apply ReLU activation function to that, and I again go for another fully connected layer from which I take the output. Is it your output of what? Output of encoder. Okay. Now as you can see, the self-attention output is passed to what? Passed through the two fully connected layers. Okay. First layer, which is called as what? Expansion layer, which expands the dimension. After that, we give it to what? The activation function ReLU for introducing non-linearity. And then we again give it to what? Second layer, which will compress. First one will expand, understand the meanings, and then second one will compress the data back. Okay. So hence the model will learn what? Complex representations. Okay. So what is the output of this feed-forward neural network block? The transformed features which are ready to be given to the decoder block from the encoder. Okay. So there are three things here. First, we give which input? The sentence as input. Please stop. Don't sit idly like that. I will not know whether you are understanding or not. What is the first input? Input sentence. This is given to input embedding and position encoding, which where we get vector representation of the input. Here input English sentence. English sentence model kardam kaadu. So we convert them into what? Vectors. Input embeddings and position encodings. So that is given as input to what? Encoder block. So this encoder block will multiply this X with what? Weights of query key value which are multiplied where I get QKV vectors. Query key values which will understand and depicts the context of the meaning in the sentence. So what is the output of MHA? Refined representation of these tokens. Now this output is given to which block? Feed forward neural network where they expand, apply non-linearity, compress and generate what? The features, the transformed features. So input sentence converted to vectors, given to MHA, we get refined features, given to feed forward, we get what? Transformed features. Are you all clear? So this is what we have seen in the last session. Okay. Now in between this feed forward and in between or after feed forward and after MHA we have these blocks. What are they? Adding and normalizing. Okay. What do we add? Please look at the diagram. Can you see that connection from MHA to add and after add and norm to add and norm again? Yes or no? That is that QKV original input is taken and added to QKV transformed after MHA. Similarly, MHA output originally is added to the output of feed forward. That is one word processed, second word processing, both of them are added. Hence parallelism takes place. Okay. On top of that, what do we see? The output, that is the transformed features after the encoder block, which is given to what? The decoder. Can you see that? Can you see this connection? This is nothing but the output of encoder which is given to what? The decoder block. Are you all clear? Okay. Now what does residual connection? What are these residual connections? That connections between what? Before MHA to after MHA. Another residual connection before feed forward to after feed forward, that is adding and normalizing. Why do we use that? Helps in better gradient flow and avoid what? Vanishing gradients. And why do we normalize the data? For stable training. For stable training. Normalizing the features, the machine will not understand that one feature is dominating the other feature and so on. Okay. So for stabilized training, we use what? Normalization. Okay. So what is the final output of the encoder? The transformed features. Now, do we have only one encoder block? We have stack of encoder. So the classic transformer architecture has how many encoder blocks? 6. Same way classic transformer has how many decoder blocks? 6. So this process that we were talking about is processed in 6 layers and the output of the encoder will be output of the last encoder block, which is the 6th layer block. Okay. So the final output is called as Z here. The input was what? X. The output of the encoder is what? Z. Okay. Now that Z contains what? Contextualized representation of the source sequence. What do you mean by source sequence? The input sequence. When I say convert English to Hindi, So source is English, target is what? Hindi. When I say convert English to Telugu, source is what? English, target is what? Telugu. When I say convert French to German, source is what? French, target is what? German. Is that clear? So what is the output of the encoder? Contextualized representation of the source sequence. Now this output is passed to what? The decoder for further processing. Are you all clear with this encoder? Yes or no? Okay. So multi-head attention, feed forward. Multi-head attention will allow each token to attend to all the tokens in the input and understand the context of the word in the given sequence. Whereas feed forward network will introduce non-linearity and transforms the given input sequence. Okay. So are you all clear with this first part of the diagram? Yes or no? Okay. So what did we see in the first part? Inputs, positional encoding, word embedding, given to MHA, passed to add and norm, given to feed forward, passed to add and norm, generate the transformed features. Are you all ready to understand decoder now? Okay. Now look at the decoder block. As I told you, in encoder we have two blocks, MHA, feed forward. But in decoder we have three sublayers. What are they? Can you see? One is called what? Masked multi-head attention. Second is what? Multi-head attention. Third is what? Feed forward. So what is the difference that you see in the encoder block and decoder block? First difference, 2 layers in encoder, 3 layers in decoder. Out of those 3 layers, 2 are same. Out of those 3 layers, 2 are same. Only one is different. What is that one which is different? Masked multi-head attention. I told you know what is masking. What is masking? Hiding the data. Did you understand what is masking? Now listen to what I am telling very carefully, which is the heart of the transformer. Okay. Now, generally, how does machine learning model gets trained? Forget about transformers for now. How does machine learning model gets trained? By understanding data. By understanding what? Data. We have input data, we have output data. I told you about 4 terms. X-train, Y-train, X-test, Y-test. What is X-train? Input data given to the model for training. What is Y-train? Output data given to model for training. Such that looking at X-train and Y-train, my model or my machine learning model will understand, oh, for this input, this would be the output. For this input, this will learn. When I talk about training data, the model learns from the training data. So what I am doing now is training. What I am doing now is training. Okay. So how do I train? I give you the question, I give you the answer. Hence you are learning. On Monday, what are we going to do? Testing. So in testing, do I give both question and answer? I give only question and I want you to write the answer. So that question is called X test. What you write is called Y prediction. What you write is what? Y prediction. What is Y test? My answer which I already know. Or the key to that answer. Are you all with me? What is X train? Input training data given to the model for learning. What is Y train? Output data which is given to the model for training. So how is model getting trained? With both input and output. How I test the model to check if the model is performing well or not? By testing. How do I test? By hiding Y test. By hiding Y test, give only X test and check the answer of the model which is Y prediction. How do I evaluate and know your performance? By comparing what? Y prediction and is already checked up. Yes or no? The same thing happens here also. What am I giving to the encoder? The input. Let's say we are talking about English to Telugu translation or English to Hindi translation. Okay. Now what is my source sequence? What is the input here? English. That is I am ASHA. That is given to which block? Encoder. But the model should learn, right? So when the model should learn, I have to give my output also. I should give my output also. That is target sequence. So when I say I am ASHA, Nenu ASHA is my target sequence, which will be given as input to the decoder. Which will be given as the input to the decoder. Are you all with me? So what is the input to the decoder? Target sequence. What is the input to the decoder? What is the input to the encoder? Source sequence. That is input. Source input is given to encoder, output is given to decoder. Now, using this encoder and decoder, the model will get trained or the transformer will get trained. Are you all clear with this? Yes or no? Now look at that right hand side diagram. What do you see in the bottom? Outputs. That outputs are nothing but the target sequence. The output is nothing but the target sequence. What am I doing with this target sequence? Same like what I have done for encoder. I am generating tokens. After I generate tokens, word embeddings of that, position encodings of that, and now that is given to what? Masked multi-head attention. Why am I masking it here? Because this is why predictions. Only for training I use it, but for testing I have to mask it. So I'm going to, which attention we use here? Masked multi-head attention. I mask the words which I want to predict next. Is it clear, everybody? Yes or no? Are you understanding? This is first change. Okay. Now let me repeat this. What is the input to the encoder? What is the input to the decoder? The target sequence. What do we do with that target sequence? Tokenization, generate word embeddings, generate position embeddings, and give it to what? Masked multi-head attention, where we again have QKV. Same thing. Let's say this is Y. Target sequence is what? Y. What is the input sequence? X. What is Z? Output of encoder. What is Y? The input to the decoder, which is the target sequence. Okay. Now I generate WQ, WK, WV for the masked multi-head attention. Multiply them with what? Y. Y into WQ will give you Q. Y into WK will give you K. Y into WV will give you V. Now again I generate new QKV values from where? From masked multi-head attention. What was the input to masked multi-head attention? WQ, WK, WV. What is the output of masked multi-head attention? Q, K, V. What was the output from the encoder block? Z. Are you all with me? Yes or no? Now listen to my second important point very carefully. Okay? Look at the diagram. Look at the diagram. In the second block that is MHA, where are the three arrow marks coming from? Observe it very carefully and give me the answer. Look at the second multi-head attention block. Where are the three arrow marks for the multi-head attention input coming from? Very good. Two are from features. One is from masked multi-head attention. And now listen, this is the heart that was talking about. When I talk about QKV, if suppose I want to find out my video on KMIT Vista channel. Okay. So how do I do? Transformer ASHA, KMIT. These are the three words. So this is query. These are what? Query. So when I do give this query, I have 10 videos getting displayed. Encoder architecture introduction, transformer architecture introduction, transformer encoder instruction, transformer decoder for both PS and NPS. Up to 6 videos displayed. So this is key. What is query? These 3 words that I gave. Transformer, ASHA, KMIT. What are the key that I get? Those 6-7 videos on my name. Transformer and ASHA KMIT, other videos of mine also will be displayed. What would be the value? The exact one which I was looking at, I'll click on that based on the keys generated. Yes or no? Now here, when I want to convert this sentence to that sentence, I am looking at the key value pairs from the encoder and query from the decoder. Query from the decoder, key value pair from the encoder, match this query with this key value and generate the output or generate the translations. Are you all with me? So when you look at those 3 arrow marks in the decoder MHA, query is from masked multi-hit attention, key values are from encoder inputs. Are you all with me? Sorry, encoder outputs. Okay. Now look at how translation actually happens. Now model is trained with I am ASHA, given as input to encoder, Nenu ASHA, given as input to what? The decoder. The model is trained now. ASHA ante ardhamaindi, I am ante ardhamaindi. Okay. Next, in the next sentence, ASHA is teaching. And the model gets trained with what? ASHA ante person. He is teaching and teaching is again trained with another some sentence and say answer is depicted. So this ASHA is known to the model. How? From this query generated from where? The decoder block, where the query have the meanings which are depicted from this English sentence which are generated from what? Key and values of the encoder block. Hence when you give the new sentence also, the model will generate the meanings. Okay. So what is this second block inside decoder? Multi-head attention, where the inputs for the multi-head attention are QKV, where Q is generated from masked multi-head attention and KV are generated from features of the encoder or the output of the encoder. Now again this process is same. What is this process? Now this MHA will understand the context, understand, oh this meaning ki, idi meaning ga. This translation word is this. And this MHA will understand, add and norm again, give it to feed forward again, it will generate the output. Did you all understand this? How translation happens? The model is getting trained with what? Input and output, where input is given to the encoder, output is given to the decoder. Once encoder and decoder inputs are processed, we have another masked multi-head attention. Sorry, we have another multi-head attention which will take the new input sequences, compare them with what? Key and values from the encoder, query from the decoder and generates the outputs. Are you all clear with this? Yes or no? Now look at the diagram for 2 minutes and understand it very carefully. Mask, token and position encodings, MHA, QKV arrow marks. Okay. Given that to add and norm, feed forward network, add and norm, the output. Those outputs from the encoder are given to what? MHA. Only KV from this is given to MHA, that is second block of the decoder. Where in the decoder I have output sequence taken as input. Again given to masked multi-head attention, given to what? Add and norm. Again given to what? MHA, where Q will be taken from decoder, KV from encoder, again add and norm, again feed forward network, again add and norm. So the output of the decoder would be translated tokens. Sorry, translated vectors. Translated vectors. Input to the encoder is vectors, that is numbers. Output from the decoder is again numbers. But numbers is the urkuntara. I am ASHA ante 0.001, 1.2.1 and urkuntara. You have to convert those numbers back into tokens. For that we apply linearity, apply softmax and then generate what? The output. So after decoder, what do you see? The output of the decoder is again given to linear model. Output of that again is given to softmax and from there we generate the final target sequence, which is the output. Are you all clear? Yes or no? So this is the architecture of what? Transformer decoder. Okay. Now we have seen how the heart and soul of transformer is what? Attention mechanism. The heart and soul of transformer is what? Attention mechanism. So we have seen already how attention mechanism works. Q, K, V would be generated. First I consider Q and K. What is that Q and K? Query, key. They will be first multiplied, that is matrix multiplication, where we get Q into K transpose. Scaling that means what? Divided by square root of dk. What is that dk? Dimension vector of each word that I am taking. That is again applied to what? Softmax function. That is again applied to what? Multiplied what? V. So Q softmax of Q K transpose divided by square root of dk into what? V is the formula for what? Attention. This is only one attention. But when I talk about MHA, this attention block repeated for multiple heads. Okay. So what is step 1 in attention? First we have X. Okay. I am explaining this for the last time. Please understand that. What is that X blue boxes that you see? Dimensional vector. Akkada 8 boxes unnai. Ante one word is depicted is what? 8 dimension vector. That is multiplied with what? Don't look at me, look at the diagram and understand. Okay? Step 1 దగ్గర X blue boxes. Okay? This X blue box is what? The dimensional vector. Okay? Each word will have. Okay? When you talk about this, each word is depicted into what? N-dimensional vector space. And what is this one? Weights generated for random weights which are generated for what? Q. So what am I doing in the beginning? I am multiplying this X with what? WQ with which I am generating what? Q. What is Q? Query of first word. Transformer ASHA KMIT is my searches, right? So first word that I am searching is what? Query. Okay. Next. What do I do next? This X again is what? Multiplied with what? The random weights generated for K. So we get what? Key for the first word. After that, what do I do? Same X multiplied with what? WV with which I generate what? Okay. So what is the output of the first block? Q, K, V. Okay. Sorry. Can you see that Q, K, V in the bottom on the left hand side figure? Yes or no? That is step 1. Can you please see this diagram here? Can you see this? This step 1 is this one I am talking about. Now what am I doing in step 2? Q, KT. Q and KT. Can you see this step 2 here? Matrix multiplication. That is Q into K transpose. What does Q into K transpose do? Finds the relationship between what? First word and second word. Are you all with me? Next, what is step 3? Look at the what is step 3? Scaling. What do you mean by scaling? Dividing this QKT with what? Square root of dk. What is this dk? The dimension vector that I have taken here. Okay. This is called scaling. What is step 4? Masking. Do I do masking in the encoder MHA? Where do I do masking? In the decoder. So for now masking is not required. So what is step 4? Softmax of what? Softmax of this one. Q K transpose divided by square root of dk. What am I doing in step 5? Look at this step 5. Matrix multiplication of what? Softmax of Q K V transpose divided by square root of dk into V. Can you look at this step 5? What am I doing in step 5? Softmax of Q K transpose divided by square root of dk into V, which is what? A. What is that A? Attention output of one block. Okay? Which is what? Read this. Attention of first words with the first value of words. I got only one word represented now. So when I talk about multi-head attention, what do I mean? Look at this. This X is concatenated with what? 3 words. First word, second word, third word. So 3 heads here. Okay. So what is the output of this? Q1, Q2, Q3. Similarly, K1, K2, K3. V1, V2, V3. When I talk about I am ASHA, I go for 3 heads. I go for what? 3 heads. Are you all with me? Okay. Now, what is this A1, A2, A3? concatenation, multi-head attention of all the words, which will be again normalized to single vector, which is processed. Okay? Got it? So multi-head attention takes what? Q, K, V and generates what? A. And generates what? A, which is concatenation of multiple heads. A1, A2, A3 concatenated will give you what? A. Okay. Now when you look into this diagram, what is the first block? MHA. This is how MHA is obtained. What are these residual connections? X plus layer of X. What do you mean by X plus layer of X? Input plus MHA of that thing done. Similarly, when I talk about another residual connection, X plus layer of X means what? Input plus feed forward of that input being done. So what is the formula that I used for residuals? X plus layer of X. What does this layer represent here? Layer represents either MHA or layer represents either feed forward. Are you all clear with this? Yes or no? So inside architecture we have multi-head. This is this. This is the residuals, and then finally we have feed forward. So what are those feed forwards? Feed forwards are nothing but the multi-layer perceptrons. Is that clear, everybody? Yes or no? Okay. Now let's talk about language translation example, which we have already started in the last class. But we have discussed only till what? Encoder. Now we will expand that to decoder as well. Okay. So what is the input sentence that I want to process? I ate an apple. So what do I do first? What do I do with that? Tokenization. What do you mean by tokenization? What do you mean by tokenization? Yes, this is my sentence, I ate an apple. I do tokenization where I split that into what? I ate an apple EOS. What is that EOS? End of sentence. That is, my sentence is ended here, such that the decoder will take the conversions and start working on its own now. Okay. After tokenization, what do? I have generated each word. For each word, I want to create what? The k-dimensional vector of each word. Okay. Now, can you see these blue boxes? Yes or no? They are what? The n-dimensional vector space generated for each token or each word. What do I do after this? I have to consider positions, because I ate an apple is different from apple ate an I. Which is the correct sentence? Because this should be given as what? First, second, third, fourth positions. If the positions are changed, the meaning of the sentence would be different. Hence I give what? Position encodings. So how am I giving the positional encodings? With respect to what? Sine and cos. Okay. Why are we using this sine and cos? Because I want to represent the sentence type. I want unique for each position and I want them to be bounded. So considering these three parameters, we use what? The sine and cos wave for generating the position encodings. Okay. So what is the formula that we have seen for position encodings? Position IDX of token in the input sentence. Okay. So when you look into this, 2i means what? If I is 0, 2 into 0 is 0. If I is 1, 2 into 1 is 1. So I am using sine wave for even tokens. I am using 2i plus 1 for odd tokens. That is sine wave for even number token generations. Cos wave for odd number token generations. This is what we have already seen. Okay. Now look at this. So I have taken input sentence, converted that input sentence into what? Tokens. I have given that tokens to embedding layer where each token is converted to what? N-dimensional vector space. Now I have generated the positions. These are what? The positions. Now what do? Look at this diagram. I have generated input embeddings, I have generated positions. Now I am doing what? Adding what? The input embeddings with what? Positions. Hence, this is the concatenation operation that I am doing on what? Embedding layer and positions, with which I generate this output. What is the? See, I call this as E1, I call this as E2, I call this as E3. What would be this? P1, P2, P3. What is this? EP1, EP2, EP3. Which are given to what? Which are given as input to the encoder block. Are you all clear? Yes or no? Okay, so we are done with what? We are done with what is tokenization, we are done with input embeddings, we are done with what? Positions. That is, we have covered till this. Okay, so what is next block? This block is called encoder block. This block is called decoder block. Okay, now what is the need for encoder block? I am processing the inputs, but I don't know what does each input mean. So to understand the context of the words in the input, to understand what? The context of words in the input, we use what? Encoder block. Okay. So what am I doing here? I am processing one input and comparing it with itself, and also processing the input in layers such that learning and adding to the context will happen. Okay. Now what would be the output of the encoder block? Contextually rich embeddings. Contextually rich embeddings. So what am I doing in attention block? What am I doing in attention block? First I generate Q, K, V, and then I perform what? Q, K transpose. After I perform what? Q, K transpose divided by square root of dk, and then I apply what? Softmax of what? Q, K, V, Q, K transpose into dk multiplied with what? P. This is formula, you will understand MHA mechanism. Okay. What do I do next? I'll understand what is query, what is key, what is value. Query is what? Search for the information. Keys are what? Interact directly with the queries and distinguishes what? One object from the other. What are the values? The actual details of the keys and queries that are generated. Okay. Now look at this. What is query? Q. What is key value store? QK transpose. What is key again? Softmax of this. What is this value? Softmax of this into V. Now look at this. MHA is what? Multi-head attention. Okay. So each word, as you can see, I will have one attention, A will have one attention, Ant will have one attention, Apple will have one attention, EOS will have one attention. Are you all clear? So for each word I generate what? QKV values. Are you all with me? Yes or no? Okay. Now, what is this? Q, which is compared with what? K. Q into K transpose, right? Yes or no? So, అందుకనే I have this multiplication symbol. Q is multiplied with what? K transpose. So, what is the output here? Q, KT. QKT given to what? So, I have removed that square root of dk. Can you see this in the top? Dimension across QKV have been dropped out for brevity. What is the dimension? Square root of dk I have removed. Okay. Just for understanding. Removed ante formula nunchi kaadu. Okay. Now what am I doing? So this is what? This is what? Q, K transpose, which is given to what? Softmax. So what is this now? Softmax of Q, K transpose divided by dk. Now this is given to what? This is again multiplied with what? V. Can you see this V? Yes or no? Now, what am I doing in this diagram? What do you see? Look at this. This Q is multiplied with K transpose. This Q again multiplied with K2 transpose. This Q is multiplied with K3 transpose. This Q is multiplied with K4 transpose. Means what? Query is one word. I am checking for this one word with all the keys. With all the keys. Are you all with me? Transformer, ASHA, KMIT. So first transformer code would be searched in the entire thing, and whatever the videos of KMIT Vista with transformer would be displayed. So this query, first word of query is compared with what? All the keys. Are you all with me? Yes or no? In the second stage, what am I doing? This query is again compared with what? K4. This query is again compared with K5. This is one multi-head attention. So similarly, we will have multiple heads and multiple encoder layers. So E diagram or same diagram. What is the difference between this diagram and this diagram? This is what on the left hand side? This is what? Single head attention. This is what? Single head attention. What I was talking here is what? This is what? Multi-head attention, where I have multiple single head attentions concatenated together. Are you all okay? This way I have parallelism because I am taking all words at a time and comparing the queries with all the keys. Okay? So we are done with what? We are done with tokenization, we are done with input embeddings, position encodings, query value and attention. Now what do you mean by self-attention? Comparing one word with itself and understanding the dependency or context of each word. Now read the sentence. What is the sentence here? The animal don't cross the street because it was too wide. Now what is this it represents here? Whether is this it representing the street or whether it representing the animal. Okay, so we have two depictions. We know it is street, but machine should understand it is street. For this we apply what? Self-attention mechanism. Attention is for understanding the context. Self-attention is for depicting the dependency of one word with the other word. So self-attention. This is called as what? Conference resolution. Okay. Now, what is this multi-head attention doing? Multi-head, how many heads do we have? That depends on what? This is very important. So the output of the multi-heads depends on what? D model and the number of heads we take. Okay. What is D model? Dimensions. Let's say 128 dimensions I have taken and 8 heads I have taken. So what would be the size of D heads? 128 by 8, which is what? 16? 16. Is it clear, everybody? So 16 times the multi-head attention will get processed. Is it clear? Okay. So after multi-head attention we have what? Feed forward network. So in feed forward network, what are we taking? We are taking the input, we are adding that with what? Normalizing layers. So by using feed forward, we introduce non-linearity, we understand complex relationship and learn from each other. Okay. So what do you mean by normalization? Finding the mean, calculating the standard deviation and understanding in what way one word is different from other word. In what way one word is deviated from the meaning of the other word. Okay. Now, when I talk about encoder, do I have only one encoder? No. I have what? Stack of multiple encoders. So this is your entire encoder functionality. So how does that happen? From output of encoder 1 is given to input to encoder 2. Output of encoder 2 is given as input to encoder 3 and so on. So what would be the final output of the encoder? The ith layer. If I have 6 layers, after 6th layer I have my final output. This is about encoders. So we have completed till what? The encoder part. Now when I talk about decoder, what do I first discuss about? Masked attention. Now let's see that. Okay. What is masked multi-head attention? The first block in the decoder. What is the first block in the decoder? Masked multi-head attention. Now let's understand that. Okay, now look at this. What is the input sentence that I am taking here? Sadhvi Chappandi. I like plants, which is in which language? English. So what is the input source? I like plants, which is in English language. Now look at the decoder. Ich mag Pflanzen, which is in German language. Okay. So what is the target sequence here? German language, which I am giving to what? Input to the decoder. To which block? First block, which is what? Masked multi-head attention. Now, what I know the words. What are those words? I like plants. So first I convert which word? I. So when I am converting this first word I still don't know the meanings of this, right? So what do? I mask them. Can you see? I have generated only first word. I am masking these two words. Are you all with me? Yes or no? Once I process first word, what do? I process second word. So appudu em chestanu? I mask this. When I am processing third word, what do? I mask fourth, fifth, sixth, whatever the words that I have. Is that clear, everybody? Because feature words I don't know. So I have to mask what? Feature, because I want to predict them. I know what are they. I know whitest. I have to predict them. Hence I go for what? Masking the feature tokens. Hence which type of attention mechanism are we using here? Masked multi-head attention. Are you all clear why do we use masked multi-head attention? Yes or no? Okay. Now let's get back to our original thing. Okay. So what are we doing here again? We take the source sentence. Now what is the first block here again? Output embeddings and positional. So first convert them into tokens. Here I have SOS, EOS, which means what? See, when I take encoder, I have I, 8 and apple, EOS. I is the first word, 8 is the second word, apple is the third word, and an ending. But here conversion takes place, right? So start of sentence. First starts with what? I am starting. After that, first word conversion, second word conversion, third word conversion, and then finally n words, and then I say end of sentence. Are you all clear? Now? Okay. So first I convert them into tokens, and then what? Embedding layer and positional encodings, and then I finally generate what? Targets. Now this targets would be given as input to what? Masked multi-head attention. Where in masked multi-head attention, what is happening? What are these? Q, K, V are multiplied with what? These tokens that I have generated. So these tokens are multiplied with what? W of Q, W of K, W of V, with which I generate what? QKV of what? Decoder. QKV of what? Decoder. Are you all clear? Now look at this. First SOS, after that SOS, first word, after that SOS, second word, SOS, third word, SOS, fourth word. So here I am asking what? All of these words. I know this is the input sentence, but what am I doing? I am masking them. So which part am I masking? The upper triangle. Which part am I masking? The upper triangle. Why am I telling you this? Is because in the coding, MHA block you have to use TRIL function, which is what? Triangular upper triangular masking. Is that clear, everybody? Yes or no? Now, when I am doing this here, am I processing them parallelly? No. One word is getting converted at a time. What will happen if I do it parallelly? All these words will have the output. Then where is the process of conversion? Please understand this point very carefully. I want conversion word by word, where I want to mask the future tokens, but I want parallelism. So what do? What do is, read this point. Outputs at a time t should pay only attention to outputs until time t minus 1. That is, masking should be done. But I want parallelization. For that, we use this concept called teacher forcing. Teacher forcing ante I have this age, I have this sentence. Okay, when I don't do masking, is there any difference between all 7 processing? There is no difference. Actually, the processing should happen this way. Which way? This way. One word at a time. But I want parallel processing like this. But parallel processing is not giving any meaning here. So what I do is, I replace this upper triangle. I replace that upper triangle with what? Activation function. Where I replace those repeated masked words with infinite symbol. Or I replace them with 0 or some notation by introducing softmax function. Okay? So I replace them with what? Infinity. Masked words with what? Infinite. When I apply softmax to that infinite, I'll get what? 0. So in this way, when I have all zeros, I am processing all the 8 bits parallelly, but I am getting only the required translations. Are you all clear? Yes or no? Okay. After that, I again go for what? Adding and normalizing. I again go for self-attention. MHA. After masked multi-head, I have MHA. Now understand 2 points here. Okay. So I am introducing 2 points which are very important for your objectives tomorrow. So in the entire transformer, I use 2 types of attentions. How many types of attentions? 2. One is called self-attention. Second one is called cross-attention. What are they? Self-attention and cross-attention. In encoder NHA, Q, K, V are from the same block, right? So this is called self-attention. Okay? When I talk about decoder, in masked multi-head attention, Q, K, V are from the same place, right? So here also it is self-attention. In the decoder MHA, Q is from decoder, K, V are from encoder. So that is called cross-attention. Okay? So now answer to my question. In the encoder MHA, which type of attention is used? Self. In the decoder masked MHA, which type of attention is used? Self-attention. In the decoder MHA, what type of attention is used? Got it? Why are we calling it as cross-attention? Because the decoder MHA will take Q and K from decoder masked MHA, KV from. Are you all clear this? Are you all clear with this? Okay, look at this. This is what I am talking about. The encoder will have keys and values from encoder. Decoder will have what? Queries from the decoder inputs, whereas keys and values from the encoders. Are you all clear? Okay, so this is K, V, this is what? Q. Got it? After that again we do what? Normalization, adding. So how many normalization adding blocks? One here, second one here, third one here. So the entire transformer architecture, how many adding and normalizing? 30. 6 encoder layers, 6 decoder layers. In each encoder, 5 times. Sorry. In for one encoder, 2. For one decoder, 3. So I have what? 5 times for one encoder decoder layer. So I have 6 such encoder and decoder layer. So 6 5s are 30 times I have to go for what? Adding and normalizing. Okay. So we don't have one decoder, but we have what? So one decoder output would be taken from all the decoders. Okay. Now after that, the output of the decoder is given to what? The linear layer, which is again given to what? Softmax, from where we get the final outputs. This is the linear layer, this is the softmax layer, from where we generate the final outputs. So where did we start till? We have started at tokenization. We have understood input embeddings, position embeddings, residual. What are these residuals? X plus layer of X, Q, KV generation. How are we generating QKV? X into WQ, X into WK, X into WV. Add and normalizing, encoder, decoder, attention mechanism, self-attention, masked multi-head, normal multi-head. What is this decoder and decoder attention ante? This is second MHA. The second decoder MHA is also called as what? Encoder decoder attention. Why? Cross attention or encoder decoder attention or MHA of decoder, all are one and the same. And then finally output probabilities by applying softmax function. So there are few architectures only on encoder decoder, there are few architectures only on decoder, there are few architectures only on encoders also. Is that clear, everybody? Did you all understand? Okay. Now we were talking about a data set, right? Yes or no? Okay. Now let's understand that in detail. Okay. So what do you mean by corpus? The data set. What is the difference between the data set and corpus? Numerical values in the data set antamu. For natural language processing task where we take text data, we call it as what? Corpus. So how many sentences am I taking? 3. What are they? I drink and I know things. When you play the Game of Thrones, you win or you die. The true enemy won't wait out of the storm. He brings the storm. So I want to train with these 3 words. I want to test the model with 1 word and check whether the translation is given properly or not. Are you all clear? Yes or no? So first I want to find the unique words. I want to find the unique words. Why do I have to find the unique words? Because I want to remove the repeated words, such that if I have repeated words, what will happen? When I am giving positions or when I am giving word embeddings, first if I have I am ASHA, I am teaching. So first word will have different word position and different word embeddings. Second I will have different word embeddings and different word positions. Is that required? This I and this I are the same. So I want to generate unique words. So how do I generate those unique words? I generate that unique words by count of set of n, with which I generate unique words. So how many unique words are generated in the sequence? How many unique words? 23. So what am I doing now? For all those 23 unique words, I am giving the numbers. This is called what? I am not giving position encoding. I am just giving what? The encodings. Encodings are assigning the random numbers in sequence to all the words. Okay. Now, this is the input sentence that I want to process. Madam, అక్కడ 3 ఉన్నాయి ఇక్కడ 1 ఉన్నాయి ఏంటిది అంటే ఆ 3 డేటా సెట్ ట్రైనింగ్ కి వాడేది టెస్టింగ్ కి I am testing what with only 1 word. I want to check if whether it is giving correct translation or not, because the model is already trained on those 3 sentences. Okay. So what is step 1 here? I am taking this input sentence. Okay. So what is step 1 for the input sentence? I have to generate what? N-dimensional vector space. So in the original paper, what is the size of DK? 512. But for an ease of understanding, what am I taking? 6. So what is my DK here? So each word when is depicted into 6 vectors. U is depicted into 6 vectors. Play is depicted into 6. Similarly, all the other words. So I am done with this part. What is this part? Taking each word and giving the n-dimensional vector matrix representation of each word. So I am done with this part. What do I do next? Find the position encodings. So how do I find the position encodings? By using these 2 formulas. So for every word I have to calculate. For when I take the word embeddings, I apply them in the formula, I get what? P1. So similarly I will do it for what? P1, P2, P3, P4, P5, P6. So this is what I have done. In the previous step I have done this, in this step I have done this. Now what do? I have to add. I have to add what? this input embeddings with what? Position encodings. So this is the position encoding matrix. This is the word embedding matrix. Are you all with me? What am I doing here? Adding. So this is the output which would be given to what? This would be given as encoder to the input as what? X. Now this X would be multiplied with what? WQ, WK, WV. Okay. Now this is that X that I got, which is multiplied with what? Weights for query. What do you mean by weights for query? WQ. Similarly, this is what? X into WK. This is X into WV. So when I am multiplying, I generate what? Query key value. That is Q, K, V. Now, what do I do? Q into, look at this, matrix multiplication of what? Q and K transpose. So this is the output. After that, what do I do? Scaling. What do you mean by that scaling? That output that I got divided by what? Square root of dk. So what is the dk here? 6. So I am generating a new vector. What do I do with this new vector? Give it to what? Give it to what? Softmax. So what will that softmax do? Generate an output. That is again multiplied with what? V. Can you see this V? QK transpose divided by square root of dk with softmax multiplied with what? V. This is the output of what? One scaled attention. When I talk about multi-head attention, what will happen? Can you see this concatenation? Can you see this concatenation? Yes or no? Okay. Look at this. This is what I got. Now I have to concatenate all such blocks and generate a final matrix. Now this matrix is called what? Output of MHA would be normalized. Would be normalized. Okay, look at this. How do I do normalizing? X plus layer of X. What is that X? Word and position encoding. Look at the diagram. Look at this diagram. This is what? Layer of X. This adding and normalizing is doing what? X plus layer of X. This X is what? Input and positional encodings. See this? Can you see this? X plus what? Layer of X. What is this layer of X? Output of multi-head attention, with which I'll generate what? New matrix. Now this new matrix is given to what? Normalizing. Meaning and mean generation and standard deviation. I've added that, normalizing it here. Okay. So how do I normalize? Value minus mean by standard deviation plus error. Okay. After that I give it to what? Feed forward. In feed forward, what am I doing? Linear layer plus ReLU. What do you mean by linear layer? Linear layer. X into W plus B. What is ReLU? Max of 0, x. What does ReLU function do? Negative values would be converted to 0. Other inputs would be processed as it is. Okay, look at this. Matrix after add and norm step is multiplied with W, is multiplied with, added with what? Bias term. This is the final value. This is XW plus B. That is 1FC1. First linear layer. What do I do after this? That linear layer is given to which function? ReLU function. So this is the output of FC1. That is activation function applied to linear layer 1. Now that is given to what? Adding and normalizing again. So first I add and normalize, calculate standard deviation and mean, and then finally I generate another matrix. Okay. Now this is the output of what? The encoder. Okay. Now what do we do in decoder? What do we do in decoder? Same thing for the other output, but here the output sequence is what? The target sequence. I repeat the same steps again. What do you mean by same steps? Look at that. Calculation is same as what? Encoder. So I will not explain those calculations again because I clearly explained you them. Okay? So what is the new thing in decoder? Masked multi-head attention. After masked multi-head attention, what do we do? MHA, which is same, again feed forward, which is the same again. Okay. So the last add and block will result the what? The resultant of the decoder. So how is the matrix here? 2 by 2 matrix or n by n matrix. But the word should be generated in sequence. So we perform flattening at the end. That is, I give it to the flattening matrix. Itla undi kada manaki 6 by 6 matrix. I want words. So I flatten them and then I generate my outputs. So what is the decoder block doing? Decoder block will have how many sublayers? 3. What are they? Masked multi-head, multi-head cross attention, feed forward neural network. Each of these layers are again followed by what? Layer normalization and residual connections. Okay. So what is the input to the decoder? Input to the decoder is from 2 places. What are those 2 places? Target sequence, which is Y, and then encoder output, which is Z. X is encoder input, Z is encoder output, Y is decoder input. Okay. So how does masked multi-head attention works? The input target sequence Y is embedded and positionally encoded. That is passed through attention mechanism. Look ahead mask. What do you mean by look ahead mask? The triangular matrix is applied in look ahead mask and I am processing that. So what is masked cross ahead attention? Queries from the decoder self attention output, key and values from the encoder output are taken and they are applied to what? Masked multi-head attention, where what will happen? It will learn which parts of the source sequence are important and what is the meaning of them from keys and values. Okay. Now finally, what is that block? Feed forward, where we have 2 connected layers. FC1, ReLU, FC2. The first one is called expansion. Apply ReLU to that and then go for compression. So what is the output of FFN block? The transform features that are sent to the next decoder layer. What do you mean by next decoder layer? Stacked decoder layers. Okay. So what are the additional components? Same, adding and normalizing, that is the residual connections. So what is the final output of the decoder? The decoder block is stacked n times. The final output of the decoder is again sent to what? The linear layer and softmax to generate the probabilities of what? Vocabulary tokens. So tokens are taken as inputs, converted to word embeddings, given to what? MHA feed forward network. This is encoder. Here I get features which are again given to what? MHA of decoder, features of KV, Q from what? Masked MHA. These are compared, given to what? FF. Here I have linear. Here I have softmax. Here again I am generating tokens. So these tokens are English language. These tokens are Telugu or Hindi language that I choose. Okay. So how many blocks? Masked multi-head, FFN. Allows decoder to attend all the previous tokens. Allow decoder to attend the relevant tokens. Introduce what? Non-linearity and transformation. Okay. So this is all about what? The total architecture of transformer depicting what? Encoder and decoder. Are you all clear with this? Okay. So it's 11:15. Take a break for 10 minutes. Assemble back. So we'll resume the class with the coding. Okay. So what did we see before the break? We have seen the architecture. We have seen how each and every word would be processed, how tokens are generated and all the remaining steps. Okay. Now we'll use that analogy and then complete the exercise part now. Okay. So what are we going to do today? Neural machine translation using what? Transformer. I am trying to take a input sentence and convert that into another language. Okay. Now, what is the sentence that I want to process now? I am taking a sentence what? I love AI. So what is my input sequence? I love AI in English. What is my output target that I want to generate? In Hindi. So when I say I love AI, what is the Hindi conversion translation of that? Mujhe AI pasand hai. Okay. So this is what I want to do. So when I give I love AI to the machine should generate what? Mujhe AI pasand hai. After the training is done. Without training, even machine can't do that. Okay. So what do I do first? I generate the token IDs for each word. I generate the token IDs for each word. Okay. So for I love AI, for mujhe pasand hai also I have generated tokens. Why am I generating tokens for Hindi sentence here? Because this Hindi is given as input to what? The decoder part for training. Okay. This is first thing. Second thing you can ask me, Madam, I love AI ki positions 1, 2, 3 undal kada. Why are the positions given as 12, 25, 52, 99? Can somebody answer this? Not random. Because corpus, data set lo etla undo sentence. This I may be somewhere, love may be somewhere, AI may be somewhere. But the sentence that I am processing is what? I love AI. In the previous example, in the corpus, we have seen 3 sentences. Okay? So the token IDs here are not randomly generated. The corpus may have so many words. I am picking up this word for testing my model. Please understand this. Corpus lo chala undi oka paragraph, oka Wikipedia data undi corpus lo about AI. Model is trained with all that. So appudu word embeddings are generated sequentially only. Okay, so akkada let's say the sentence is something like, artificial intelligence is all about this and I am in love with artificial intelligence. So I may have some position, love may have some position, AI may have some position. So I am training my model with that paragraph. Now I want to test my model by giving 3 words. So which are those 3 words I am giving? I love AI. Are you all with me? So that is the reason I have some random tokens here. Okay, are you all clear with this? Data set is something. I am using this sentence from the data set for conversion. Hence, I have this random tokens. Okay. Now, I am generating tokens for the source language, which is English. I am also generating tokens for the target language, which is Hindi, because the input to the encoder is the source language, the input to the decoder is the target language. So, hence I am generating the tokens for both of them. Okay. So, after that, what do? I generate the embeddings, word embeddings for each token. So, I love AI, mujhe Hindi pasand, mujhe AI pasand hai. So, what is the size of the dimensional vector that you see here? 4. Madam, oksar 512 antaru, oksar 8 antaru, oksar 4 antaru. Yes, the dimension is up to the programmer. Tomorrow also in the exam, we will give you consider dimension as what? 128 or consider dimension as 256. You have to read that in the question and write. A question చదవకుండా గుడ్డిగా ఏదో ఒకటి తీసుకుంటే మీ టెస్ట్ కేస్ పాస్ అవ్వదు. Are you all clear with this? You have to declare your dimension as per the question that we give. Then only your test case would be passed. The code is exactly the same, but I am not getting the output. My test case is not passed. అని చెప్పడానికి లేదు. Are you all clear with this? Okay. So I am generating the 4-dimensional vector for each word. Okay. So I have generated the position. These are encodings only. I didn't calculate position encodings yet. I have generated the encodings of each word. I have generated the word embeddings of each word. Now I'll generate the position encodings. How do I generate the position encodings? With those 2 formulas, sine and cos for even and odd. Okay. After that, what do I do in the bottom? Can you see that? Final embeddings are what? Adding word embeddings and positional encodings. So the first one is word embeddings and I'm adding that with position encodings and generating a new matrix. So what is the input sentence that I am processing here? I love AI. So can you see that last bottom rows? I is equal to 0.1 plus 0.01. What is that 0.1? That 0.1 is a word embedding of I. What is that 0.01? The position encoding that was calculated for I. So both of them are added and I got the resultant and was 0.11. Is it clear? So I am generating word embeddings and calculating position encodings. I am adding both of them where I get the resultant matrix, and now this matrix would be given as input to what? Encoder. Okay. So that X input, do you see that X input? That X input is nothing but this resultant matrix that I got. Okay. Now what do I do in attention, self-attention encoder? I'll calculate scale dot product attention. That is, I'll multiply what? WQ, WK, WV with X inputs and generate what? QKV. So Q is X input into WQ, K is X input into WK, V is X input into WV. After I calculate QKV, what do? I calculate attention mechanism. So what is attention mechanism? Q into K transpose divided by square root of dk. Okay, I am doing that. What is this dk? Dimension. What was the dimension that I have taken here? 4. So into square root of 4, that is will happen what? 2. Are you all clear? This is called as attention score. After I do this, what will I do? I'll apply softmax function and multiply that with what? The value. This is attention mechanism. Now this attention mechanism will be multiplied to what? Multi-head attention. So X input was my original input. X was my original input. X input is what? The embeddings generated. Okay. Now I give that to what? Multi-head attention. So when you talk about multi-head attention, I have QI. What is QI? For first block, it is Q of 1. For the second head, it is Q of 2. For the third head, it is Q of 3. That number of heads also we will mention. Number of heads also we will mention. We will mention the dimensions, we will mention the number of heads. So suppose I have 512 dimension and if I have 8 heads. So 512 divided by 8, which is 64 times it will be processed. Okay. So xi is equal to what? Xi is equal to x final into WQI. The same process would be repeated. Again, like as you can see, attention of QI, KI, VI means what? Multi-head attention applied. On what? QI, K transpose by square root of dk into VI. Okay. So after I do that, I concatenate what? All the attention blocks with which I will be completing my multi-head attention. Okay. Now after that, the output of multi-head attention will have the next block, which is what? Feed forward. So what is FF1? ReLU of W1 into attention weights, attention output plus B1. What is FFN2? W2 into FFN1 plus B. Are you getting? MHA feed forward. MHA output is given to what? FFN1. W into X is what here? MHA output plus B. Okay. Secondly, I have FFN2, that is equal to what? FFN1 into weights plus B. So with this I will be done with what? Attention block. Encoder block. After encoder, what do I have? Decoder. In decoder, what is the first block? Masked multi-head attention. So I again generate QKV for the decoder. Okay. And Q is generated from the previous decoder. KV are taken from where? Encoder outputs. The encoders. Okay. So is the formula changed here? Yes. Why is the formula changed? I am adding masking here. So what is the formula here now? Softmax of Q into K transpose divided by square root of dk plus masking into V. Are you all clear with this? Okay. Now, what is the formula for encoder, decoder attention or cross attention? Softmax of Q of decoder into K transpose of decoder by square root of dk into V of encoder. Are you all clear? QKT, where Q is taken from where? The decoder. Hence I am writing it as what? Q of decoder. KT is taken from where? Encoder. So KT of encoder. V is taken from where? Encoder. So what is the formula for cross attention? Q decoder, KT of encoder divided by square root of dk into V of encoder. So same attention but three different formulas. For encoder we have softmax of QKT by square root of dk into V. For masked multi-head attention in the decoder we have softmax of QK transpose by square root of dk plus masking into V. For this we have softmax of Q decoder, KT encoder by square root of dk into V of encoder. So are you all clear now? Got the difference between three attentions. One is self-attentions in decoder, which is masked multi-head. One is self-attention in encoder, it is the normal one. One is cross-attention of encoder and decoder. So can you see the name? What did I put there? I didn't keep it as MHA in decoder. I kept it as what? Encoder-decoder attention, or we simply call it as cross-attention. Again we have feed-forward where we have what? ReLU of W1 into output of MHA plus bias. FFN2 would be what? W2 into FF1 plus B2. Okay. So the final output of I love AI would be what? One word generated. Mujhe AI pasand hai. Is that clear everybody? Okay. Now let's get back to the code. Okay. So as I told you, we are not developing transformer from scratch, but we are using which module? PyTorch. PyTorch library. In PyTorch library, we are using NN module. Which module are we using? NN. Okay. So first, okay. So what are we doing first? We are importing the required necessary libraries. Okay. So I am using PyTorch and the input that I am taking is text data. Hence, I first install which library? Install torch text. So inside the torch library, PyTorch, we have this text module. As my input sequence is test, I import this. There are different versions again. Incompatibility issues with Python will be there. Hence, torch 2.0.1, torch text 0.1.2, 0.15.2 are the versions that I am installing. This would be done in prior. Don't worry about all this. Okay. Okay. Now these are the three libraries that I am importing. What are they? Torch, torch.nn as n and torch functional as f. So what does torch nn dot do? Provides what? The neural network layers. Am I doing forward propagation, loss calculation, backward propagation, all that? No, because I'm not doing it from scratch, but I'm using which module? NN module. Okay. Next, what does torch.functional do? Provides the activation functions which are softmax and ReLU. Where are we using softmax? Where are we using ReLU? Softmax inside MHA, ReLU inside feed forward. For that I am importing what? NN.functional. Okay. Are you all clear with the libraries? Now let's implement encoder block, decoder block. So first what do? I am done with this importing. I am taking two sentences. What are those two sentences? English to which translation? French. So rep meeku edanna ivvochu mem. Don't worry about. Does that matter? Does not matter. Okay. So we may give you any length input sentence. You have to write the code. Okay. So we will give you English sentence. We will give you one translated sentence for that. Meeku language rakunna em kaadu because we are only giving you the what? Input and output, that is target sequence and source and target sequences. So what do you do first? Import libraries, take that input. After that what do? Tokenizations. What do? Not tokenizations, word encodings. What are we doing? Word encodings. So here I do tokenization. First is libraries, second is data input, third is word positions for all the words, next is tokenization. So how am I doing tokenization? By splitting the given sentence. By splitting the given sentence. What is this sentence? The sentence that I am performing, the sentence that I am taking here, by what? Word mapping. So I am processing the sentence and word mapping and doing what? Tokenization. Now the output of tokenization is what? Can you see here in the bottom? 1, 2, 3, 4. So there are 4 tokens which are generated. I love AI along with one padding, which is EOS sentence extra. Got it? Did you understand this first block? Any doubts in this first step? Look at the code very carefully, and if you have any doubts, you can ask me now. Any doubts here? Yes or no? No. Next, this is the same thing. I have depicted it block by block. So what do I do first? Position encodings. What do you mean by why position encoding is required? Because transformers do not have what? Inherent understanding of the word order. So if you want to generate proper translated sequences, you have to give your input sequence in order, for which we do what? Encoding. Why are we doing encoding ante? What? RNNs will store the positions, but your transformers are not storing the positions. We give the word embeddings and then process. Okay. Now look at the code. Okay. So what are we doing here? See, these first 3 lines would be same for every model. Okay. Defining a class called position encoding and inheriting which module? NN dot module. So what are the parameters that I am passing here for that? D model and max length. So what does D model represents? The D model will represents what? The dimension of the token embedding. That is the size of the vector of each token that we have taken. Okay. So in our case, what is the dimension? I'll let you know about it. Don't worry for now. What is that maximum length? I may give you 4 length sequence, I may give you 5 length sequence, or I may give you 10 length sequence. So that maximum length I am declaring with some random value, which is 5000. మీరు 10,000 పెట్టుకోండి, 2,000 పెట్టుకోండి, 5,000 పెట్టుకోండి, that does not matter because we are not processing that big sentences. We are processing only 5 or 10 words. Okay. Now look at this. Look at the first line here. The first line starts with self dot encoding, that is equal to torch dot 0 of max length and D model. This is torch dot 0. What are this torch and 0 tensors is what I am telling you now. Basically, we are generating the word vectors, right? So when I generate the word vectors, your NN module will not understand those word embeddings. So each word vector should be converted to tensors. So when you are importing PyTorch module, you have to convert everything into tensors. Okay. So torch.0 will generate an empty vector, all zeros initially. So when I am processing the sentence, I want to process word with what? The word embeddings. Word with the word embeddings. So how many words do I have in I love AI? I love AI. 4. I love AI with end of sequence. Okay, I will have n-dimensional vector, love will have n-dimensional vector, AI will have n-dimensional vector. So what is the maximum length of the sequence? 4. So that is what I am trying to depict here. Okay. So torch dot zeros of max length. Maximum length is maximum length of your sequence, comma what? D-dimensional. So maximum length is 4. So for every word I have to use what? D dimension. That is what I am doing here. Are you all clear? Yes or no? Okay. Next, what am I doing? Next, what am I doing? Torch dot arrange. Arrange all the words in the sequence till the maximum length starting from 0. Are you observing? Torch dot arrange 0 comma what? maximum length and unsqueeze them. Unsqueeze them is converting the adding one extra dimensions because I'm considering them as what? Tensors. Okay. So this torch.arange creates a tensor starting from where? 0 to the maximum length. Are you all clear? Yes or no? After that, what am I doing? After that, what am I doing? I am dividing a term. Why am I dividing that term? Because I want to divide the entire sequence into odd and even. So what does that divide term do? This is the factor basically which we are using for scaling. What are we using it for? We are using for scaling the position encoding to make the encoding higher dimensions decay more slowly than the lower dimensions such that I divide them into even and odd. Even and odd. Are you all clear? We are dividing that by 10,000 into I. Do you remember that formula? That is the divide term here. Okay. Now what are the next two lines? Self-encoding with sine and cos positions into what? The divide term that I have taken such that even position and odd positions word would be separated. Are you all clear? Yes or no? So here I is the index of the dimension. I is the index of the dimension. 0, 2, 4 even terms. 1, 3, 5 odd terms. Are you all clear? So after that I am encoding that particular sequence and unsqueezing that. Okay. Now when I talk about unsqueezing it here, what do you mean? I want to convert that back into normal vector. I want to convert that back into normal vector. Okay. So make a note of it. Unsqueeze of 0 will add extra dimension at the start of encoding. Unsqueeze of 0 will add an extra dimension at the start of encoding to make it more compatible for broadcasting when we add that input embeddings to the forward pass. Okay. Now, what do you see after that? What do you see after that? Can you see a function called define forward? Yes or no? Can you see this define forward? What is this express self of encoding? I am adding my word embedding with what? The position encodings. X is the word embedding. Self dot encoding is what? The position encoding. So, in the previous case, I have generated the word embeddings. Here I am generating my positional encoding and adding them. Are you all clear? Yes or no? So, what you observe here is every block will have two parts. First part is the class that we are defining. Second part is the forward function where we implement that particular class. Okay. So, this is all about position encodings. So, I want to print two things. What are those two things? Positional encoding values and final input after adding positional encodings. Okay. So these are the positional encodings where I have E values and all that. After I add them to embedding vectors, I have the final matrix. Now this would be given to what? The encoder as input. Okay. Now let's get back to multi-head attention. So what is the formula for multi-head attention? Q into K transpose divided by square root of dk into. Okay. So that is scale dot product. Only one attention. When I talk about multi-head attention, multiple heads taken into consideration. Now look at this. What are the models that we pass? K and V. Yes or no? K and V. So can you see here? D model divided by number of heads. In multi-head, we take phi 12 as sequence. If suppose I take D model is equal to phi 12 and I have 8 heads. So I divide what? K and V with what? D model with number of heads. So phi 12 divided by 8 is what? 64. If I take 128 divided by 8 is what? 16. So 16 times I process my K and Q values. Are you all clear with this? Yes or no? Am I taking self dot D underscore Q? No, because the output of encoding values K and V are only given to what? The decoder. Are you all with me? Yes or no? Okay. Now, how am I generating query key values? By using which model? Linear model based on what? D underscore model. Yes or no? This QKV also should be a matrix. This matrix should be matching with what? The dimension vector. So self.query, self.key, self.value with respect to which module? NN dot linear module. So with this I implement what? MHA. What is MHA? Multi-head attention. Okay. Now Q values are generated, K values are generated, V values are generated. Okay. Now I again apply this to forward block. I apply this to what? As I told you, one is class, one is forward. Now observe this forward very carefully. Okay. So what am I doing in forward? First I generate QKV. And then I calculate attention scores. What are these attention scores? Matrix multiplication of what? Q into K transpose divided by what? Square root of dk. Okay. After this, I don't use masking. I apply what? Softmax of attention scores. Softmax of Q trace K transpose by dk. And then I calculate final output. What is the final attention output? Matrix multiplication of what? Softmax of QK transpose by dk, which is attention weights into V. Are you all clear with this? Yes or no? What is attention scores? QK transpose. Attention scores is QK transpose divided by square root of dk. What is attention weights? Softmax of QK transpose divided by square root of dk. What is final output? This into what? V. Got it? This is what? MHA block. After MHA, what do we do? Feed forward network. Here also same thing. I am defining a class. I am defining init, super method. I am calling two layers. What are those two layers? FC1 and FC2. What am I giving in FC1? D model and DFF. In FC2, what do I give? This output DFF with what? D model. So this is the class. Again in the bottom I have forward function. In this forward function I am returning what? FC2. What is that FC2? ReLU of self.FC1. Are you all clear? Yes or no? FC2 is what? ReLU of FC1. Next I'll have encoder. Encoder also same thing. I'll define class, I'll define forward function. So in encoder layer what do we have? Multi-head, feed forward, norm 1, norm 2. So I am declaring all that here. Self.multi-head, self.feed forward, self.norm1, self.norm 2. In forward I'll put them in sequence. So what do I do first? Multi-head with what? X. X is what? The target sequence. After that I apply normalization with what? X plus layer of X. What is that layer of X? This attention output. After that I go for what? Feed forward. After that I go for what? Self.norm of X plus FF output. X plus layer of X. Are you all clear? This is the build code for what? Encoder. So every block, positional encoding, class, forward function. MHA class, forward function. Encoder class, feed forward class, forward function. MHA class, forward function. Okay. Now after this what do I have? Decoder layer. Please look at this decoder layer. Same thing. I have class, I have forward. In class what am I doing in decoder? Multi-head attention 1. What is this multi-head attention 1? Masked multi-head attention. What is multi-head attention 2? Encoder, decoder attention or cross attention. What is feed forward? Feed forward layer. How many normalization blocks here? 3. Norm 1, norm 2, norm 3. Now look at the parameters. In multi-head attention 1, I am passing D model and number of heads. Feed forward D model DFF. Here D model, D model, D model.
Okay, now look at the forward function. What comes first in decoder? Masked multi-head attention, which is given as what? Multi-head attention N1, in which what am I passing? X comma what? Target mask. X comma target sequence. After that, I apply norm1. What is the second block? MHA, where I am giving what? X comma source input. After that, adding and normalizing again. After that, feed forward norm3 and then return X. Are you all clear with the decoder? Yes or no? First is class, second is forward function. Now this is the transformer model. So in transformer model, what do we have? X, encoder, decoder, linear, softmax. Yes or no? X input given to transformer, output of transformer encoder, output of transformer encoder given to input of decoder, output of decoder is given to linear softmax. Now look at this. Same thing again here. Class, forward. In class, what am I doing? I take input, embeddings of the input, position encoding, encoder layer, decoder layer, final output, which is nothing but the linear output. Okay. Now look at the forward. First I give source input to the position encoder, target input for the position encoder of what? The decoder part, which is target. Here source means what? Encoder. Here target means what? Decoder. Okay. Now first I pass my encoder, then I pass my decoder, and then I finally calculate my output, which is taken from the decoder output. Is this clear, everybody? So this is the entire transformer model. Okay. Now here you need not say about encoding block and decoding block, because we've already declared them. We are calling those blocks here in the transformer model. Are you all clear with this? Yes or no? Okay. Now after I do transformer model, I'll try predictions. Okay. Now when you look at the predictions, look at this. First I take the input sequence, tokenize that input sequence, add an extra dimension by unqueezing, and then what is this torch dot trill? Masking by upper triangle. In which block? MHA block. Okay, can you see this? Generates a mask for what? The target sequence. Can you see this? And then I'll take the target sequence, target torch dot and zeros, and then I'll take the transformer model, which I've already called, and try.
I'll put MHA and feed forward into what? The encoder layer. After this I do what? Decoder layer. After that I'll build my transformer model. After that I am doing the predictions. Now look at this last one. What is this last one? Initializations that I was talking about, which will be deferred for your code tomorrow in the labs. Okay. So what does this D model represents? Dimensional vector for each word. What is this number of heads? Number of heads means multi heads that I am taking. Okay. Number of layers means what?
Number of encoder layers and number of decoder layer. The classic transformer has 6 and 6, but 6 and 6 takes time for processing, hence we take what? 2. That may be deferred tomorrow again. Is it clear? So you have to initialize what parameters? D dimension, number of heads, number of encoding layers, number of decoding layers. Are you all clear? With this we are done with understanding which architecture? The transformer architecture. Okay. Any doubts?